regularity structure. So on Friday, we start really to talk about regularity structures. And so again, feel free to ask questions. So I know that's a very difficult topic. It's maybe the most difficult in the field right now. And so I also don't understand everything. So I have a lot of gaps. So really feel free to ask questions, even if you think it's a stupid question. So I had really at the very beginning, I had a lot of, well, I wouldn't say stupid doubts, but well, I wasn't even able to formulate what was my doubt because I didn't really get anything. So really feel free to ask questions. It's not easy what we're doing here. So, okay, so the last time we really started to talk about the regularity structures, and okay, so there's this kind of example that we have, this KPZ equation. And so recall that, so this is now a revision of last class. One of the main results says that this sequence of equation converges, where C epsilon here is a sequence of constants going to infinity, which in particular kind of implies that this, without the C epsilon, does not converge. In other words, this equation seen as a function of the noise, as a function of psi, is not continuous. So psi epsilon converging to some psi does not imply that the sequence of equations converges, or the sequence of solution converges. It does not imply it. It's not a continuous function of psi. And so basically the big goal is to find out, well, what do we need to know more about the noise? What additional information do we need to know, such that given this additional information, we then obtain a continuous function of the noise and maybe some of the additional information that we add. What I mean with this is, well, a priori, we only know that psi epsilon maybe converges to psi. What happens if we would know that psi epsilon converges to psi and maybe some nonlinear functions of psi epsilon also converge? Yeah. So if this would be true, well, then the sequence of equation converge. And so the idea is to find these kind of nonlinear functions, or these functions of the noise psi epsilon, that would guarantee convergence of the sequence of equations. That's the whole goal. And that's, of course, not easy. I think there was a comment.
So, for example, we would like to see the solution as function of these new objects that you construct from.
Yeah. So, and so again, just a revision. So what did we do? I mean, just to get a feeling, we can still do a PK iteration. So we kind of check on what, I mean, how does the solution, if it exists, but how does the solution look like? And so we did a PK iteration, starting with our initial guess, which is 0, or the initial condition. Let's say it's 0. So then plugging H0 into our fixed point map that I wrote on last time. So the first approximation is K convolved with psi, which is the solution to the linear equation. So that's the first approximation. So then you plug in the solution to the linear equation. So this guy into your fixed point map. You check what it does. It gives the same term again, plus this. So then this would mean that the solution would be described by, or approximated by, this term and this term. Yeah? So for this term, we introduce more graphical notation. So H is K convolved with psi. So if we take the derivative, it's K prime convolved with psi. This is what this means here. It's K prime convolved with psi. Derivative of K convolved with psi. This we square. This is what kind of this means, that we take 2 copies of this. And this we convolve with K. So this tells us that, well, a better or probably better approximation of the solution is a function of, well, this guy and this guy. And then we continue. We plug this sum into the fixed point map, and well, we compute. And then we get this. So the point of view of regularity structures is that, well, the solution to KPZ must have this form. something like this. There's some expansion. Must have this form. So what was our original problem? Our original problem was that okay, so this is well defined. So K prime convolved with size well defined, but now we're not allowed to square it. There was a result which says you are not allowed to do this. You're simply not allowed to do this. There's no canonical way of doing this. This was this result. Yeah. Because there's too low regularity. So this we're not allowed to do. So the point of your regularity structures is, well, let's ignore this for one moment. So we ignore this problem for one moment. At some point we need to face it, but let's ignore it for one moment. Let's assume these kind of symbols exist. Okay. And so we know that every solution, or this solution to the equation, can be written kind of as a function of all of these guys. We don't know yet what they are because, well, they're not well defined, but let's assume they exist for some magical reason. Yeah. The idea is then that, so these are basis vectors. Yeah. And now you look at all functions that have this expansion. This is a certain space of function. And it turns out that in this space, you can formulate a fixed point problem, which you can solve. Okay. And then, of course, in the second step, what you need to do is, at some point, you need to face the problem of that, well, that you need to define these guys. Yeah. So you need to define this guy, which is not a problem. This guy, that's a problem. This guy and all of the other guys that come with expansion. And it turns out this we can do with stochastic methods called renormalization. Okay. But really the first step is to view them as basis vectors. Yeah. So let me just make one comment. If it would be true that KPZ would be a continuous function of the noise, essentially what it would mean would be, well, if this converges, so if this converges, then also all of these higher order objects also converge. If it would be a continuous function of the noise. It is not a continuous function of the noise. So if this converges, which with this I mean something like this, it does not imply that this converges or that this converges. Okay. However, what turns out is our equations are so-called subcritical. What turns out is that, well, we can't guarantee that convergence of this implies convergence of this. But what we can do is we can try to prove that this converges. Then we do something to this object, which is called renormalization, which is kind of subtracting the stuff that makes it diverge. We do something similar here. Also, we try to subtract the stuff that makes this diverge. We do this for a bunch of symbols. And it turns out that after a certain point, if we have renormalized this and this, after a certain point, all the higher objects do converge. Yeah. And basically, if you look carefully, if you compare this guy with this guy, I mean, graphically already, this guy is somehow contained in this guy, yeah? Because if you just look at this, yeah, it is almost the same as this. The only difference is that here this kernel is K. And this kernel is K prime. Yeah, but they're basically the symbols really contained in this. Yeah. So this would be the first instance where you would have hoped, oh, if this converges, so I know essentially that this converges, maybe the whole object converges. In this case, it will not be true. Yeah. But what turns out that the next object will be kind of built out of this one, out of this one, out of this one. Yeah. And once enough of these simpler objects converge, also the higher ones will converge. It's not trivial to see this, not at all. That's what's happening. This is an effect of subcriticality. Okay. So then we defined a regularity structure, which has three elements, A, T, G, where A is an index set, which essentially just lists the orders or the homogeneities, the regularities that can appear. The second thing is T, which is a graded vector space. So it can be written as this kind of direct sum of these T alphas, where each T alpha is a vector space, finite dimensional. And T alpha is simply the collection of objects of order of homogeneity alpha. And finally, the last thing, G, is a group of linear transformations satisfying a certain property. That's the regularity structure. Okay. Okay, so then last time, what we did, we started to have a look at the regularity structures of polynomials, which is kind of should simply serve as an example. Yeah. So for the regularity structure. So that's kind of one of the first examples one classically sees, where the index at A are the natural numbers, T are the space of all polynomials, let's say D plus 1 variables, x0, x1, x2, to xd. Yeah. T alpha are all polynomials of order alpha, meaning that the order of the multi-indices is alpha. Yeah. This is the T alpha. Where, just as a reminder, if K is written in this form, K0, K1, K2 up to KD, and this symbol Ks is 2 times K0 plus K1 plus K2 up to KD. And the order of this monomial, or this object, is defined as, well, the multiplication x0 to K0, x1 to K1, and so on. So this is our T alpha, all polynomials of degree alpha. Okay. So what is this G? Well, all elements of G are of this form gamma ZZ prime. And essentially what this gamma ZZ prime does, it kind of recenters the polynomial. We'll see in a second why this is, why we need this. Yeah? So this is really the definition. Yeah? So take the polynomial and recenters it around the point Z prime and Z. Okay, so, yeah.
I have a question. We need to verify a property for this group, right? That when you subtract x from gamma x, it gets lower regularity, right?
Yeah, yeah, basically. So what you need to check is this. Check. Is that gamma? Okay, that's it. Prime. X to the k minus x to the k has degree less than k.
Okay, now it's obvious. So
yeah, exactly. So now, I mean, now you multiply this out. One term is really of the form x to the k, and this you subtract. Yes, yes, yes. That's really coming from that.
Thank you.
Welcome. Okay. So this is this regularity structures of polynomials. A's are the natural numbers. T are the polynomials. T alpha are polynomials of order alpha. And these gammas take this. Okay. So now let's think how a typical element of this regularity structure looks like. It's a question. Yeah? How does a typical, and here was typical, I mean interesting. So interesting for, well, our purposes. Element of T look like. Okay. So, okay, so T is a polynomial, but the kind of polynomial that you are usually interested in is the following. So answer, question and answer. So typically what we're interested in is the following. So assume you have some kind of Hölder continuous function, yeah, alpha positive. Yeah. So then we define an element of T like that. Capital F of Z, yeah, is the sum over all k as less or equal than alpha, 1 over k factorial, kth derivative at position z, x to the k. Huh? Okay, so I don't know what it reminds you, but it should remind you a little bit of Taylor polynomial. Yeah? So if you remember Taylor's theorem, then okay, so Taylor theorem tells you that a sufficiently smooth function you can approximate with a polynomial. And what are the coefficients of these polynomials? Well, exactly these guys. Yeah? So in the sense, this is really something like the abstract version of the Taylor polynomial. Okay. And one note, so this is also good to train a little bit the notation we introduced. We had these projections where Q0, for instance, is the projection of the element of the regularity structure on the zeroth order term. What is the zeroth order term here? So that's projection. On T0. What is the zeroth order term here? Well, it's simply the function f, right? So this is really just so that you can train a little bit the notation. Okay, so this is how a typical element looks like. So now, I mean, it's called regularity structure. So it must have to do something with regularities. And well, if we have a function f and c alpha, we already know how to measure regularity. So we talked about this. What I would like now to do is to see if we can kind of recover the regularity criteria or the definition that we had for the c alpha functions using this new notation of regularity structure. Yeah. So basically the question is the above regularity structure helpful to measure smoothness of f? To measure smoothness of f. Maybe. Yeah, okay, can be like this. So let's see. Let's see. So I will now do a computation, and maybe at the beginning it's not clear what I will do, but I hope that at the end you kind of understand why I did the computations that I did. Okay. And so let's only look at the zeroth order component. We can calculate. So again, it would probably not be clear what I'm doing now, but I hope that in like 5 minutes it will be clear. So just trust me that what I'm doing now makes sense. So let's do this, look at this guy. So maybe just to give you an idea already, I want to measure smoothness. So smoothness always has something to do with comparing the function f at two different values, z and z prime, z bar. Yeah? And that's essentially what I'm trying to do. And the interpretation of this gamma guy here, it's kind of a recentering. I mean, so this is a certain polynomial, and then I do a recentering from z bar to z. So let's see what happens to then. Gamma z bar sum ks less or equal than alpha 1 over k factorial dk f of z bar x to the k. Yeah. Now these gammas are linear, so I can interchange sum and the gamma. So let's see. So that's the sum k s less or equal than alpha 1 over k factorial dk f of z bar. And then here I have gamma z bar x to the k. Okay. So the next step is to apply the definition of gamma. Next step is to apply definition of z of gamma. Ks less or equal than alpha 1 over k factorial dk f of z bar. And now here x minus z bar minus z to the k. Okay. And so now the next step is to sum this out. I mean, to write more concretely down what this guy is. Yeah? So let me, this I will copy better. So this is the sum Ks less or equal than alpha. Then the sum over all j less or equal than k, where less or equal simply means component-wise less or equal. 1 over k factorial dk f of z bar. And so this will then be something like k choose j, x to the j, z minus z bar to the k minus j. Okay. Okay, so I hope you could follow a little bit. Essentially, what I did is to apply here the definition of gamma and then to expand this expression, which is hopefully correct. So now, okay, so now what I would like to do is I would like to look at the zeroth order component. Yeah, so Q0 of gamma z bar f of z bar. Okay. So what this simply means, if I write this, that in here I pick j equal to 0. So this is, and here we pick j equal to 0. So that's a sum over ks less or equal than alpha 1 over k factorial dk f of z bar. If j is equal to 0, this is equal to 1. Okay, this is my this would be the term 1, constant 1. And this is z minus z bar to the k. Z minus z bar to the k. So this here now is a number. And the thing is that this number is the, how do you call it? Not exponent, component. Well, it's what is essential. So this is a polynomial. And in front of x to 0, we multiply with this number. So there's a much more elegant way of saying this. Okay, so now let's see. So now what do we have? Thus, and now it's getting interesting. I want to measure smoothness. And I am claiming that what makes sense is to look at this difference. And I've kind of to prove it. So, okay, what's happening here? F is a polynomial. This is a polynomial. It's a polynomial. Well, they have a certain degree. And what we will do now is we compare. So if you have a polynomial of the form sum ak xk, how do you call these?
You compare the coefficients, right?
Coefficients. Thanks. Exactly. Thanks. So, I mean, both of these guys are polynomials, and what we will do is we will compare the difference of the coefficients. Yeah. So we kind of fix a certain degree that we want to look at, yeah, and then we compare the coefficients. And in this example, we simply compare the coefficients of degree 0. Yeah. So what do we have then here? The coefficient of this of degree 0 is my f of z. Yeah. So let's just remember what is f of z, right? So here the coefficient in front of x to the 0 is f of z. It's this guy. the coefficient of x to 0 we calculated here, it's this whole sum. So it's sum ks less or equal than alpha 1 over k factorial dk f of z bar z minus z bar to the k. So yeah, so modulus sine, or maybe modulus sine, this should be correct. So maybe I messed up with the sign here somewhere. I don't know. Yeah, maybe I messed up with the sign. I guess I would expect to have here z bar and here z. So modulus sine, this is what we got. So there's probably somewhere sine problem. Anyway, if you now look at, if you now look at this difference, what is this term here? So this term, okay, so I will solve.
The expansion, the polynomial, the Taylor polynomial?
Exactly, exactly. So this is the Taylor polynomial of f. Taylor polynomial at f. And it turns out that if f is, so I never commented on this very clearly, but this is something you can think of. If f is, okay, C alpha, and then you subtract the full Taylor polynomial of it, this distance, and this has nothing to do now with the regularity structure, so it's something to do with C alpha functions. This distance is bounded by z minus z bar to the alpha. Yeah. So I hope you kind of believe this, the last fact. But the important thing is that by looking at this guy, what appears here is really the Taylor polynomial. And that's why I looked at this guy initially. Because in this way, in this framework, I really recover kind of the usual way of studying smoothness of a function. Yeah.
What are trying to convince us is that you can use the regularity structure to define the regularity.
Exactly, exactly. And that this is really that this kind of expression is the correct expression to look at.
But what about the other terms?
Well, you can do the same calculation that I did here. So you see, now you can look at Q1, Q2, Q3, and then you need to check what are the coefficients that you get. And for instance, if you look here at something like 1 instead of 0, what you would get here is, for instance, the derivative. And then this term here would become the Taylor polynomial of f prime. I see. And then, the bound you would have -1.
I see.
That's a computation.
So basically, we just, to define the regularity, you just need to look at the 0 order coefficient.
No. You need to look at maybe in this specific context. Well, here we know already that f is C alpha, but in general, you also need to look at the higher order terms. Okay. This was just an example. It's kind of the simplest example I could come up with. To look at the 0 order term. And so there's actually a theorem which says the following. So it's one of the first theorems in the original paper. Let A, T, G be the regularity structures of polynomials, be the regularity structure of polynomials. Yeah, and let's say alpha positive. Yeah. Then f is a C alpha function. Yeah. If and only if there exists a function capital F mapping r to the d plus 1 into t alpha minus, such that such that the zeroth order component of f of z is little f of z, and for all compact subsets of Rd plus 1, we have that the following expression is formed. The supremum of all z in k. We now look at the
Dirk, you are muted.
I don't know how this happened.
Oh, it's okay.
Okay. Perfect. So all this result says is that you can express or you can define what is an alpha Hölder function using the framework of regularity structures, and this is how you do it. Yeah? And okay, so this is not a particularly important result, but what you should really take from it is that if I take this regularity structure of polynomials and I look at these kind of expressions, with these expressions, I can measure regularity. Yeah. Okay.
I did understand.
Yeah, go ahead.
In the above example, I didn't understand because why we need to look at to all coefficients until order alpha.
Well, in this case, of course, not because we already know that f is C alpha.
But suppose you don't know, then you need to check.
Yeah, I think you need to check. Yeah.
Even if alpha is integer, we need to check.
Yeah, I think so.
Because my impression is that
but maybe you want to exclude the integers. I'm not completely sure. Yeah, maybe you want to exclude the integers here.
Okay.
But okay, so don't get hung up too much with all the details. I mean, okay. So what was my goal with the example is to show to you that if I compute this expression here, yeah, then I get on the right hand side something that makes sense. Because our goal is, of course, not to study the regularity structure of polynomials, but more complicated regularity structures that are derived from singular stochastic PDEs. Yeah? And so then the question is, what do we do in this case? How do we measure smoothness in this case? And we will do it essentially in the same way. We will look at expressions of this type. Yeah? So essentially, I wanted to motivate why I look at this particular expression, gamma z bar f of z bar. Yeah? Because if in the case of the polynomial regularity structure, I do it, I get the Taylor polynomial.
I see, but it's not always the case. And
well, yeah, they are more complicated regularity structures. Yeah. Where I mean, here, for instance, I know that these coefficients they are related one to each other, right? They're derivatives of each other. Yeah. This must not necessarily be the case in more complicated examples.
Is the I don't know if it's an interesting example, but what if we want to add Dirk distributions?
Where do you want to add direct distribution?
Why?
Where do you want to add a direct?
To the regularity structure. Can we? Because
sure, so yeah, so then you would kind of add a symbol that symbolizes random variable with direct distribution. So you can do this. Yeah. We will see still. So be patient a little bit. We see still to the regularity structure from a single PDE. Okay.
Okay.
Okay, so this is all of this is nice, and I would like to make one more comment. So okay, so here we have this abstract polynomial, but at some point, of course, we want to turn it into something more concrete. I mean, it's just an abstract object, and we want to turn this into something more concrete. So this is essentially the second step, and for this we need a map that takes this kind of abstract object and spits out something concrete. Yeah. This will motivate the next definition. Yeah. So goal, turn f of z, which is the sum here, into a concrete object. F of z, x to the k into a concrete object. A concrete object. Okay. So what we need is the following. We need a map that we will denote by pi z. Yeah. That goes from the regularity structures and, well, in the general case, it may not spit out a function, but maybe distribution, Schwarz distribution. Yeah. And well, in this case, it's relatively clear what this should be. Yeah. So the map that in this case, we will consider the following. So more concretely, pi z of x to the k. This will again, this will now be a polynomial function, which will be z bar minus z to the k. Yeah. So again, so essentially this map pi turns this concrete polynomial into turns this abstract polynomial into a concrete polynomial centered at the point z. Yeah. And there's an important observation. Yeah. That the Taylor polynomial of Taylor polynomial of f equals pi z f of z dot. Yeah. So I can show it to you maybe because, well, pi z f of z, let's say it's z bar. So what is this? So by linearity, it's the sum over all ks. This will equal alpha, 1 over k factorial, the k's derivative, pi z, x to the k, z bar. Yeah. Which then really by our definition of pi z turns out to be the alphas, to be the Taylor polynomial of f. dk f of z, z bar minus z to the k. So that's the Taylor polynomial of f centered at z. Yeah? Okay. So this pi turns out to be another important object in the theory of regularity structure. And so maybe there was one thing that was always wondering me, at least at the beginning, is that, well, so when you have regularity structures, there's this index at A and there's this T alpha, yeah? And for instance, in our example, we said, well, T alpha are all polynomials of degree alpha. But I mean, if you check the definition, a priori, I can define T2, for instance, to be all polynomials of degree 3. Yeah? So there, it seems to be quite arbitrary. So there's nothing that forbids me to do this. And actually it turns out that, well, you can do this. But when you want, if you want to apply with the theory, next to the regularity structure, there's also something called a model. And the model actually determines the correct choice of orders or homogeneities. So that's
what's the word? I didn't understand.
Order or homogeneity.
Order. Ah, okay.
Yeah. So definition. Okay. So let say tau, capital tau, A, T, G be a regularity structure. Regularity structure. A model for tau, yeah, on RD plus 1, RD plus 1 consists of a pair pi gamma such that, let's see. First point. Gamma is a map from RD plus 1 times RD plus 1 into the group G, where gamma of Z is the identity. And here again, so the way to think about this gamma is, say you take your polynomial, send it at the point Z, and then you recenter it at the point Z. So what you do is nothing. Gamma of Z bar applied to gamma Z bar Z hat, we want it to be equal to gamma of Z hat. And the way to think about this condition is the following. Say gamma takes a polynomial, which is centered around Z hat, and we center it around Z. It's the same as taking the polynomial, which is centered around Z hat, centered around Z bar, and then repeat this procedure. Now we have a polynomial centered Z bar, and now we center the Z. And it shouldn't matter if you directly recenter from Z hat to Z, or if you kind of take some intermediate steps. This is what this condition says. The second is that pi actually is a family or collection of maps. Yeah. So for each point in RD plus 1, we have one map. Yeah. And each pi Z maps T into the space of Schwarz distributions. Yeah. Third condition. So, and this third condition will now give a connection between pi and gamma. Yeah. So pi Z is supposed to be the same as pi Z bar gamma Z bar Z. Okay, so let's think about this. So let's see, we have say we have some polynomial, and what this guy does, it gives you the polynomial function centered around Z. Yeah. Now let's say we have this polynomial which is centered around Z. Now we shift the point, yeah, and essentially evaluate it. Yeah. And the order in which you do it shouldn't matter. This is what the third condition says, which of course then also kind of quite a lot restricts your freedom of choosing pi and gamma. So they kind of need to be in agreement between each other. And the fourth condition, and this kind of maybe the most important one when you really want to apply the theory, and which really determines the order, is the following. For all alpha in A, yeah, for all compact subsets of RD plus 1, yeah, we require the following, that pi z tau of sz lambda eta is less or equal than lambda to the alpha, and the supremum over beta smaller than alpha of gamma zz bar tau beta divided by z minus z bar, the alpha minus beta, is smaller or equal than 1. Yeah. So uniformly over tau in T alpha, lambda between 0 and 1, yeah, and zz bar and k. Yeah. And test functions. Eta and BR, where R is minus the minimum of A. Okay.
So the last condition is saying that alpha is not arbitrary.
Exactly. So the last condition is actually what determines the order in practice. I mean, so you see, you can define a regularity structure and nobody forces you to define a model, but in this way you will never be able to analyze any single Spde. So you always need to define, if you want to apply it, you always need to define a model. And really this condition is really what tells you what is the correct homogeneity or order. Yeah. I see. That's really what it is. And so that's one thing. If you look at this, and if you remember one of our first definitions of the C alpha spaces, I think in the second class, yeah, then this was something really, really similar. Yeah. So you maybe remember we looked at something like this: U test against SZ lambda eta divided by lambda to the alpha, and we wanted this to be less or equal than 1. Yeah. If we have such a condition for some distribution U, say alpha negative, then this implies that this distribution U is in one of the C alpha spaces. So this condition looks really pretty much like this, right? Yeah. And it's almost the same, but it's not quite the same. So why it's not quite the same? Well, first of all, the tau is some element of your regularity structure, like some abstract polynomial. When you apply pi z, this now turns into a function or distribution. Yeah. And what this condition says is that the only test functions to test this distribution against pi z tau, which is your distribution, are those that are centered around z. Yeah. So here and here you really take the same point. Whereas, I mean, here you have a fixed distribution and this point can vary, and will vary. Yeah? So it's almost the same, but it's not quite the same. So this condition does not imply that pi z tau is in C alpha. It's a weaker condition, which is good because it's easier to verify. Yeah?
Sorry, one question.
Okay.
In point 4, alpha is positive or negative?
Exact does not matter. So alpha can be positive and negative.
Okay.
So you're right. So in particular, this implies, and this is where a lot of efforts goes into it. So if alpha is negative, then this thing here explodes, right? And you want to control the rate at which it explodes. And when this alpha is negative, then it's really like the regularity. When alpha is positive, as alpha goes to 0, this thing will vanish, right? So you want really this to vanish. So there you see already that regularity is not quite the same as the order of homogeneity, at least not for positive alpha. It's not quite the same.
But what about the other term on the right hand side?
This one?
Yeah, this is suitable for alpha positive.
Yeah. So, but see here. So here you have alpha minus beta, and beta must be less than alpha. So this exponent is always positive. No?
But when you define the order of the distribution, we use only the left hand side.
Yeah, this essentially determines then the order. There's actually, this is in the theory result which states that in practice you only need to check this.
I see.
So hidden in the theory.
Okay.
Okay, so let me define now what we call so-called D-gamma spaces, and then I will give an example of a regularity structure for an Spde, which is maybe a bit more relaxing than what we do right now. So fix a regularity structure. Yeah. Tau. Say tau's ATG. Yeah. And the model. Pi gamma. Yeah, for tau. Yeah. Then for all gamma in R, so gamma can be negative, the space of modeled distributions, D gamma distributions, D gamma consists of all functions, f from RD plus 1 to T gamma minus, such that for all compact subsets of RD plus 1, the following norm is finite: F gamma K, which is the supremum of all Z and K, the supremum of all beta smaller than gamma, F of Z beta, plus the supremum of all Z bar and K, Z not equal to Z bar, the supremum over all beta less than alpha, gamma, of Fz minus gamma ZZ bar, Fz bar, and we look at the beta's component divided by Z minus Z bar to the alpha minus beta is finite. Okay, so I let you have a look here again. Okay, so this is the important part.
Why this needs to have less than? Okay. It makes sense to have less regularity than gamma, right? Because in the examples.
What do you mean with less regularity than gamma?
Because T minus gamma is all the irregularities below gamma, right?
Exactly.
And the white noise, for example.
Exactly. So, I mean, first of all, so this F here really exactly lives. I mean, so here we have all the T alphas with alpha, or all the T betas, maybe better, all the T betas with beta less than gamma. Yeah. And really what we measure here is the smoothness of the coefficients, right, in front of our basis vectors. So when we looked at this example here, where's this? This example here, we already measured smoothness of this, but I mean, of course, what we really do is we look at the smoothness of these coefficients. This is what determines the smoothness. Yeah. And so if you look at the definition, how do we measure smoothness? Okay, so we take the supreme over all components over point Z, now compact Z, okay. And here we have this kind of term that reminds one of Hölder continuity. And if you look at this f of z minus gamma z, z bar, f of z bar, this is essentially the same term we looked at for this polynomial regularity structure. Yeah. So it's really the same term. So for the polynomial regularity structure, these D gamma spaces are our C gamma or C alpha spaces. It's really the same thing. Yeah.
What about negative values?
Okay, so in practice, you want the gamma always be positive. But this doesn't matter. I mean, of course, you might have so I mean, so one example, whatever, you may have, I don't know, some function h1 of z, and then maybe you have something that symbolizes your noise, something we'll see in a moment. So this would be maybe something with a negative regularity. Maybe you have, I don't know, h2 of z, maybe x, h3 of z, x square, right? This could be a possible candidate. Yeah. I didn't explain it what it is. So for those who see it for the first time, this will be completely mysterious. But just think here of some symbol that symbolizes the white noise. So something probably of negative order or homogeneity.
But what would be the regularity of F? I mean, which modeled space? Which is gamma for of F? This F?
Well, here it should be
2,
maybe something slightly larger than 2.
I see.
Slightly larger than 2. And then really, I mean, so remember the computation we did. I mean, when we look at something like this, so for instance, then Q. So let's say, and okay, can you remind me in a bit about this question? So because I think what I'm now about to say, maybe not many people can follow because it.
Can you say again to remind you?
You can try to remind me later of this question because I did not really talk yet about this symbol. So maybe it's becomes a bit
I'll be patient.
Okay. So anyway, so now we have these D gamma spaces, and these D gamma spaces are kind of like an abstract version or generalized version actually of the Hölder spaces that we know. And it turns out that in these spaces, one can formulate the fixed point problem and solve it. So these spaces are much better behaved. Okay. What I would like to do now, so what we did so far, okay, I defined what's the regularity structure, I defined what's the model. We talked shortly about these D gamma spaces. Yeah. I would like now to give an example for regularity structure for an SPDE. Yeah. So I would like now to show you how you build up the regularity structure when you have SPDE. So essentially we redo the same what we did so far for the polynomial regularity structure, but for an SPDE. So like regularity structures for SPDE. Structures for SPDs. And here I would like not to talk about KPZ, but about another example. For the simple reason that in the book of Heider and Fritz, you find the regularity structure for KPZ in this note that I'm following for another equation called phi 4D. But for the example I'm showing now, I'm not sure if there are any lecture notes building up the regularity structure. Example. This is called the parabolic Anderson model, PAM, parabolic Anderson model, which is this equation. dtu is Laplacian of u plus xi times u, and here xi is a space white noise. So there's no time component, space white noise. White noise. So the mild solution, or Duhamel's principle, mild solution, is the following. It says that u is k convolved with u times xi plus k convolved with the initial condition. Okay. So what do we want to do now? So let's maybe go back to the last class. Essentially, what we would like now to determine are these basis vectors for this equation. So what do we need to describe the solution to this equation? This is the question we would like to answer. Okay. So the question is, which basis vectors are needed? Basis vectors are needed to describe u. Describe u. And what you will see is there's an algorithm for that. And I will present this algorithm. And the way to think of it is the following. So you have a left-hand side of the equation, right, left-hand side, which is this solution. Left-hand side u. And then there's a right-hand side. Let's call it f, right-hand side. Let's say f, which is really something that u times xi. Okay.
What is xi?
So xi, so I will talk about this. Xi is an abstract symbol for the noise. So it's kind of an abstract representation of our noise. So this will essentially be the basis vector that represents our noise. And the key point here is that, of course, at some point we may look at the sequence of equation, take psi epsilon. So the psi epsilon changes with epsilon. However, for whatever epsilon, we will always take the same symbol. So this represents our noise.
And the regularity is d over 2.
Minus d over 2.
Minus d over 2.
Exactly. But let's start with this slowly. So left-hand side. So what, at least the first approximation, we need to describe our solution u? Well, you may have a smooth part. For a smooth part, well, Taylor's theorem tells us we need to use polynomials. So for this, we use these symbols, 1 and x to the k, where k is n to the d plus 1. So for the smooth part of the solution, we probably need these basis vectors, or basis symbols. Okay. So what happens then? The right-hand side is u times xi. So we will need, for the right-hand side, to describe the right-hand side, we need a xi, where this is an abstract, so-called abstract symbol for the noise. It's an abstract basis vector symbol for the noise. for the noise. Yeah. And we need x to the k times xi. Yeah. So this is like 1 times xi. This is x to the k times psi. U times xi. Yeah. So again, so usually for smooth functions, the only basis vectors we would need are these. Now we can't really expect the solution to be completely smooth. So we need something else. And this something else we call xi, capital Xi. Yeah. Okay, great. So what happens then? Well, now we need to go back to the left-hand side. So now we have the right-hand side, xi, x to the k times xi. Given this, how does the solution look like? Well, what is the solution really? It's the convolution of the right-hand side with the heap kernel. Okay. So we will have an I of xi, yeah, and an I of x to the k times xi. Yeah, where this I here, yeah, it's an abstract symbol representing convolution with k. Abstract symbol representing convolution with k. Representing convolution with k. With the heap kernel k. Okay.
But the element of the regularity structure will be the full expression, right? E and E of xi and E of xk xi.
So what you need to picture here is that, yeah, these are all, yeah, exactly. So the regularity structure, we will have this, we will have this, we will have this, we will have this, we will have this. So now we gather all the things that probably we will need to describe the solution. Okay. So now we're here at the left-hand side. Now we need to go back to the right-hand side. The right-hand side was u times xi. So we need to take this guy and multiply with xi. I of xi and xi. We need to take this guy, yeah, which represents u, and multiply with xi. Okay. Yeah, so it's I of x to the k. Yes. Times xi.
Basically, we are adding all the symbols you need to do the Picard iteration.
Exactly. That's exactly it. Mm-hmm. And then we continue. Now we have a new right-hand side. To form the solution out of it, we need to take convolution with the heap kernel of the right-hand side. So we will have an I of xi times xi, right? Yes. So we take this, and then we need to take the convolution with the heap kernel. And for the convolution, we take this abstract symbol I. And this guy also convolution with the heap kernel, which is I of x to the k xi, and closing the bracket. Yeah? And then we continue. Yeah? To get the right-hand side, we multiply this and this with xi. Yeah? Okay. It's more or less clear, the logic. Okay, so we would have I of xi, and I, this I x to the k xi, and then I continue. Is more or less clear, the logic?
Well, for me, yes.
Okay.
For me also.
So, yeah. Huh, Christian?
For me also it's clear. For me.
Okay, okay. I mean, you need to accept a little bit that that we have these two additional symbols, this guy and this guy. But if you think about it, I mean, these and these, they don't also have any real meaning, right? They're kind of placeholders. They just turn into concrete objects once we make out of these a polynomial function. Then there's something more concrete. So, but in this way, you kind of get what you need to describe the solution. And this is really all you're interested in. And you're not all interested in all the possible symbols you can make of psi, I, x to the k, only those that are useful for you. So then essentially we continue like this. Continue in this way. This way, yeah. So then the regularity structure, T, is really, you take the left-hand side and the right-hand side, and it's really the vector space generated by U and F. Vector space generated by U and F. Okay. So this is T. And there was coming already the question from Guilherme, so what is the regularity of the noise or the homogeneity of the noise? And this is something we need to talk about now. So the question is, what is T alpha here? So you remember that T, we need to be able to write T as the sum of these T alphas, where T alpha are really the elements of T of order or homogeneity alpha. And in this case, of course, you could choose whatever you want. Yeah? If you're not interested in applying this, then you can choose whatever you want. Nobody can forbid you to do this. But if you're interested in applying this, then you shouldn't choose whatever you want. But you should make more smart choices. So how to do this in a smart way? So recall that psi, where we never talked about only space noise, only space-time noise. But you can do essentially the same, and the regularity is minus d half, same minus some kappa for all kappa positive. So kappa is for some reason the letter chosen in the theory of regularity structures. I guess because the epsilon is reserved for the approximation of psi. So here you need to think of kappa being very, very small. Yeah? So then in this case, we define the order of psi, of the abstract symbol of psi, is minus d over 2 minus kappa. Yeah. Then the order of 1 is 0. Yeah. The order of xi, for instance, is 1, if I is between 1 and d. The order of x0 would be 2 because time counts double. That's the time coordinate. Yeah. Coordinate. Yeah. So this would give us the homogeneity is kind of these basic symbols. Yeah. And now what we saw is that, I mean, we kind of multiply these symbols and we do all kind of stuff with this. So now we need to come up with the rule when you kind of do compositions of these symbols, how does the order behave? Yeah. So in general, we impose the following rules. In general, we impose the rule. That if you multiply two symbols, tau and tau bar, then the order is the sum of the orders. Yeah. which, if you think about it, makes sense. So for instance, x squared is x times x. So what is the order? It's 2. So it's 1 plus 1. Yeah? Which also already tells you, I mean, you can think of the order bit being like the regularity, but it's not quite the same. Huh? Because if you multiply function that is 2 times differentiable with one that is 3 times differentiable, the product will generally not be 5 times differentiable. Yeah. And well, there's one thing missing is, what about the order of I tau? Well, I should symbolize convolution with the heat kernel. And what do we know about this? When we convolve with the heat kernel, we improve kind of 2 in regularity. And to mirror that, we define the order of I of tau like this. It's the order of tau plus 2. So this represents the Schauder estimate. This represents the Schauder estimate. The Schauder estimate. Okay. And then the final definition. So T alpha is really the vector space generated by all taus of order alpha. Okay. Okay. Are there any questions? Up here. Okay. So I will ignore a little bit the gamma. The gamma is also the object I understand the least. And there's also an automatic way of generating this. But so in this way, kind of you generate all the symbols that you need. And again, so now you have, of course, the problem that, well, that's very nice, but all is very abstract. Now we would like to have something a little bit more concrete. So what I will show you now is how to construct what one calls the canonical model for this regularity structure. Yeah? Yeah. So that's the next goal. Goal is to make everything more concrete. More concrete, meaning that we want to define what is called the canonical model. We want to redefine the canonical model. The canonical model. Okay. And so for that, if you want to define the canonical model, then, for instance, we really want to find a way to make in a very concrete way sense out of this, for instance, of this multiplication, yeah, which may be dangerous, which is actually dangerous. It is not dangerous as long as this symbol psi stands for a smooth version of our noise. So let's work with a smooth version of our noise for now. So here, what we do is we replace psi by psi delta, yeah, which is really some modifier rho delta convolved with psi. Yeah. So rho smooth modifier. Okay. So let's try to define what is called the canonical model. Yeah. So the first thing, the canonical model on polynomials will act, well, in the very natural way. So we can call this maybe pi z delta. The very natural way is z bar minus z to the k. Yeah?
So for each delta, we have a canonical model.
Exactly. So you have a sequence of canonical models. So maybe that's a good thing to keep in mind. The regularity structure does not depend on delta. So you see all these symbols. There's no delta, there's no epsilon, there's nothing. These are fixed. The approximation comes into the game once you define the model. In the model, you see that you're really working with an approximation with some psi delta.
So we have a family of models.
Exactly. And what you're interested in is in the study of the convergence of the family of models.
And these objects live in some space, and you can talk about convergence.
Exactly. And it turns out that this fixed point problem that I will still mention, not today, is kind of continuous as a function of the model. Yeah. So this is it. Okay, so for the polynomials, there's nothing happens really. What happens with the noise, pi z delta psi, yeah, of z bar, it's really simply the noise evaluated z bar. So psi delta is actually a smooth function, so we can evaluate it at a fixed point, at a given point in R plus 1. Yeah? Okay. So this is maybe the natural definition. So in particular, see that this z here actually plays no role. Yeah? But it's still the natural definition. And so now, what else do we do? So in our regularity structure, what kind of things do we have? With these x to the k, we have the symbols for psi. Then we have multiplications. Yeah? So then we build symbols out of multiplication. Pi z delta tau 1, tau 2 of z bar. This we define simply at the product, yeah, tau 1 z bar times pi z delta tau 2 of z bar. Yeah. So this is something that can pop up. We have two symbols, tau 1, tau 2, then we may multiply them. And there's another thing, namely integration. So now we need to talk about how does this map here acts on this I, this symbol that represents integration. That's slightly more complicated. But let's see. So it's pi z tau I of tau, yeah, of z bar. Okay, so it is the integral of our heat kernel, k of z bar minus y, pi z tau delta of z of y dy. Yeah. So this is maybe the natural thing to do. So we take the convolution with the heat kernel, evaluate z bar. And okay, so this seems to be the natural thing to do, right?
But what if in bullet 2 we have chi, the name of the letter in English? Chi.
Yeah, I call it psi, but I'm not.
Psi for what if appears psi times psi?
So then you have a problem, and this does not work. So this only works at the smooth step. And so you identified already the problem is that, okay, so here, I mean, we take the naive product, which we can do at fixed level delta, but we will have a problem when delta goes to 0. And actually, what you will, so you have now this, what we call canonical model, but the real model that you want to work with is the so-called renormalized model, where you kind of need to redefine this multiplication. But the way it usually works, you first take the canonical model, and then you kind of redefine it.
You see where is the problem and
exactly. You know, I mean, you know already that somewhere here there will be some tau 1, tau 2 that pose problem here. So then you kind of need to redefine what you mean with multiplication. Yeah.
Okay.
So that's
And
not the
not-
final model.
And not always the same procedure can be done. I mean,
No, you need to, you need to identify where the problem. This may change from case to case. But they are very good. I mean, I think by now there's a pretty good black box that kind of tells you, that gives an almost algorithmic way of doing that.
Okay.
Okay, but let's go back to this guy. I mean, so this seems to be the natural definition, right? And well, let's go back. So I of tau. So we're saying that the order of this should be the order of tau plus 2. So for instance, if you think of here's dimension is 3, let's say, so this would be -1/2. Let's ignore the kappa. This would be -3/2. I of psi, since we add 2, should have order +1/2, positive order. Okay, positive order. How was this in definition of the model? In the definition of the model, we want to have an estimate of this form. So if alpha here would be 1/2, we would have the square root of lambda. As lambda goes to 0, this goes to 0, which would kind of impose that this must go to 0. Now let's go back to this definition here. Let's assume tau is psi in dimension 3 or 2. So this thing should have, this thing should have order 1/2. So if we now test it against some smooth scale test function, and as lambda goes to 0, this thing should go to 0. And there's no reason that this goes to 0. Why should this go to 0? So it would essentially imply that this must be essentially the 0 function. But there's no reason why this should go to 0. So this can't be the correct definition. So what we need to do is we will subtract here the Taylor polynomial of k to kind of guarantee that we will have a model. So sum over all k, s which is smaller than tau plus 2. Yeah. Z bar minus z to the k over k factorial, integral of dk k of z minus y pi z tau pi z delta tau of y dy. Yeah. So here really what we have the Taylor expansion, or actually maybe it should include the sum. Here really we have the Taylor expansion of k up to order tau plus 2.
Okay. Can you explain again why this is necessary?
Yes. In the definition of a model, in the definition of a model, you have a condition of this form, that pi z tau s z lambda eta is less or equal to lambda to the alpha if tau is of order alpha. If alpha is not positive, what happens? This will go to 0 as lambda goes to 0. Okay.
If alpha is positive.
If alpha is positive, exactly. Now imagine, let's say d is equal to 3, then the order of psi would be essentially -3/2 minus kappa. Yeah. Then from this is followed that I of psi should have order 1/2 minus kappa. Okay.
Okay. So alpha should be positive.
Exactly, should be positive. We think of kappa very, very small. Very, very small. So it should be positive. This means that if I calculate pi z of I of psi and I test it against such a test function and I send lambda to 0, it should go to 0.
Yeah. And why it's not happening in the convolution of k with pi?
Okay. So if I mean, let's assume we would have something like this. I of tau z bar. I mean, if this would be k of z bar minus z minus y, sorry. Pi, assume that this would be the definition that we choose.
Okay.
Yes.
We are taking tau equal psi.
Yeah, yeah. Then, for instance, what would be this? Pi z tau I of psi. Yeah. Now we test it against some function as z lambda eta. What is this? So here we do dz bar as z lambda eta that bar against this k of z bar minus y pi z delta psi of y dy. Yeah. So let's see what this is. Here we have two integrals. So you have s z lambda eta of z bar. Yeah. K of z bar minus y psi delta y dy dz bar. Okay.
Mm-hmm.
Okay. So let's see a quick way of seeing that there's no a priori reason why this should go to 0.
Because we want to see why this is not going to 0 with lambda, right?
Exactly.
Maybe it's good to replace the text function with
whatever it is. Lambda minus d minus 2 eta lambda to the minus 2 t bar minus t lambda to the minus 1 x minus x bar minus x and so on. So I mean, in a sense, so what should happen? So the idea is, since you get an object of positive order, as lambda goes to 0, it should converge to essentially this thing evaluated at the center point. So as lambda goes to 0, this will converge to this guy. Oops. Yeah, that's maybe the way to see it. Yeah. As lambda goes to 0. Okay. So this is true. So once this is a continuous function, you test it against something and you send lambda to 0, then it converges to, well, the function evaluated at the center point z. So you can forget all these computations I did here. Yeah. And then this condition would tell you that this must be 0. Yeah. But it turns out that this is not 0. If the definition would be chosen in the wrong way, because this would be really simply k over z minus y psi of delta y dy. And this is not 0.
I see.
And if you take this definition here, and now for z bar, plug in z. So then you have a z here. Most of these terms will simply vanish, okay? Except the term where k is equal to 0. Yeah? Where k is equal to 0, you don't have anything in front of it. And then you don't have a derivative. So then you would also have k of z minus y. K of z minus y, k of z minus y. 0. Yeah?
But so why you need to subtract everything if you subtract just the?
You want also that this happens at the right order.
Mm. Okay.
And
Somehow that condition on the model ensures that these things are bounded. I don't know if this makes sense.
Which condition do you mean?
The condition or the way we define the order in the regularity structure.
Mm-hmm. Bounded. Oh, bounded from below, you mean? Or what do you mean?
No, maybe I'm just talking nonsense, but that condition helps us to ensure that things converge, no?
You mean this definition?
The definition of order.
Yeah, okay, in a certain sense, yes. So because what turns out is that if you have these subcritical models, then conversions of the model is already applied by the conversion of finitely many symbols. And finally, so of all symbols of negative order, actually. And so that's why you don't want to have any accumulation points of order, so that you really have only a finite number of symbols that you need to test.
Nice.
So I guess that's it for today. So next time we kind of wrap up. So next time I still need to decide what I want to do. If I really will show kind of a computation of how you see how to renormalize some of these things. And then there are some things maybe still to be mentioned, like reconstruction theory and this kind of stuff. I will still think about it, how to do it best. Okay.
More questions or comments?
So at the end, we will be able to see that there's solution for PUN.
Yes.
We are going to formulate the fixed point problem now. So nice.
Yeah. I still need to think of how to test, but yes, that's the idea.
Okay. We continue on Wednesday, no? 2 days.
Exactly. Wednesday, 4 o'clock.
Thank you. Bye-bye.
You're welcome.
Thank you. Bye-bye.